What's up, everybody? In a previous video, we talked about Retrieval Augmented Generation. This is a pretty recent and powerful technique in natural language processing. It turns out that one of the key kind of inputs into Retrieval Augmented Generation is information retrieval, and that's what we're going to talk about in this video. So let's just jump right into it. Okay, so let's kind of quickly review Retrieval Augmented Generation. I have an entire video on that, and I'll link it in the description below. But basically, we have a query, so a user will have some sort of question. You use information retrieval, so you kind of have a bunch of, say, documents that the user thinks is relevant, and you compare your query to these different documents. We'll see more about that later on. And kind of the most relevant documents in conjunction with the query get input into a large language model. So in a nutshell, that's Retrieval Augmented Generation. Again, more on that in a different video. But I will say that information retrieval, the step going from like a big chunk of documents to, say, only a few that are relevant, that's a huge part of the Retrieval Augmented Generation, or RAG. And so we're going to kind of focus on that in this entire video. Of course, you might wonder, well, why should I even use RAG in the first place? Well, it turns out that LLMs, first of all, are very powerful, but they do have some shortcomings, and one big one is that they tend to kind of make up answers or hallucinate. So one way to kind of mitigate that or prevent them from doing that is to give the relevant context with your questions so that they can come up with a more aligned response. All right, so let's have a quick look at today's plan. We'll introduce the problem statement of information retrieval. We'll talk about some shortcomings from previous solutions, and then we'll talk about some more modern solutions with vector embeddings. All right, so let's jump into it. All right, so let's introduce the problem of information retrieval. So, you might guess you're trying to retrieve some information. So really we're focused on text, and you might have, say, a large chunk of text or a large corpus of text. So that just means, say, a bunch of documents. And then you might have your own query, and you want to figure out which of the texts are actually most relevant to your query. So this is the problem of information retrieval. Of course, we all know and love Google, the search engine. So this is one use case for information retrieval. But our use case will be a bit different, as the documents, say, are something that you own, and you just want to quickly sift through the documents to figure out what information is relevant. And then, of course, the main use case that we'll be kind of thinking of in the back of our head is to provide some context for a large language model. All right, so let's quickly discuss why some of the classical methods kind of fall short in terms of retrieving information from a corpus of text. So suppose you're going to make a search, and your kind of algorithm to find the relevant text in your corpus of documents is to search by keyword. Now, this is kind of a very basic search technique, and I kind of mentioned TF-IDF and BM25, so there's more sophisticated versions of this. But let's just kind of focus on this concrete example of searching by keyword. So there's kind of some fundamental issues with this approach. For instance, the keyword could be misspelled, or you might use a slight variant of the keyword that appears in the text. So these are kind of things that could cause you to not retrieve the right information. Furthermore, the keyword may appear, but it may appear in the wrong context that you really are thinking of. So you might get an extra document that's really not relevant. So we can kind of see that this simple approach of searching by keyword, or maybe some slightly more sophisticated versions of this, will definitely have some drawbacks, and the hope is that some of the methods that we'll discuss later on will kind of address these issues. All right, so here come vector embeddings. Now this is really a whole kind of deep topic on its own, but we're just going to again briefly introduce what's going on here. So you might be given a chunk of text, so I say maybe like a word, a sentence, a paragraph, something like this. You should think maybe like a paragraph, especially for the example I have below. Now I say we create a vector representation of the text. That might seem kind of foreign, but basically for this, say, paragraph, we're going to associate a list of numbers with this text, in hopes that this list of numbers actually kind of captures the context of the paragraph. So that's really what a vector representation is. But we don't have to get too much into it, and I may cover this in a future video. So let's have a look at this example here. So actually, when I say example, I mean this is from OpenAI's website. So they actually allow you through an API call to get vector embeddings. So that's pretty useful. They say in the first column how much it costs, so how many pages per dollar, and they kind of describe exactly what that means. So you can kind of see that the first one's quite a bit cheaper than the other two. The other two are comparable. So then they provide the performance on the popular evaluation data set. So you can see they're all on around, between 61 and 65. And then you see the max input, 8191. So that's pretty important. That says this is how many tokens you can input into the embedding to get a response. So a token is roughly 4 to 5 words. Really depends on exactly what you're inputting into the model. So that gives you an idea of the length of text you can really input into these embeddings. Now you may think, oh great, I can input. You might want to push it right up to the max, but you might find when you're actually working with these things that sometimes a shorter context can really kind of improve performance on your downstream tasks. So I would keep that in mind. So I just wanted to show you that these vector embeddings actually do appear. You can make API calls to them, and they're actually pretty useful, as we'll discuss moving forward. All right, I will mention that there are several ways to get dense embeddings. Dense embeddings is just another terminology for vector representations. So you may have heard of the transformer, and there's actually a couple different types of the transformer. So there's encoder, decoder, and decoder only, for instance. So for each of these, you might have different kind of techniques to kind of grab the dense embedding. So I won't get too much into this, but this kind of opens the door to get embeddings from Bert as well as GPT. I did want to highlight that, say with Bert, there are kind of multiple ways to get embeddings. So I put up a diagram here. There's two kind of things, bi-encoder and cross-encoder. So with the bi-encoder, you have two models, and each of them creates an embedding, and then somehow you compare to see how relevant they are. Whereas with the cross-encoder, you actually input both of your text into one model, and then it automatically outputs how kind of similar they are. So I will say that it's not really like a one-size-fits-all in terms of the dense embeddings, and actually there's kind of several different ways to go about it. All right, so there might be several different ways to go about choosing an embedding. So how do you figure out which one to go for? Well, I will say that the very large language models, so the ones that have hundreds of billions of parameters, they do work really well. However, they are pretty pricey. I would say if you're just working on a small project and you want to get a feel for how these things work, I would suggest just starting off with a large language model, like one of the bigger ones, and just use the API calls. They are expensive, but they aren't so expensive that it's going to run you a big bill in terms of just a small project. Really, the priciness comes in if you have a lot of data that you want to process. Now, what if you do have a ton of data you want to process? You still may end up using one of the very big large language models, but there are some other options to be aware of. For instance, you might want to use something like Bert, which is orders of magnitude smaller than something like ChatGPT. This gives you some clear advantages. The first is that it's quite a bit cheaper to run. The second is it might run on your local computer or even, say, in the cloud, but for cheap. And the third is you'll really have some fine-grained control over your fine-tuning on your own data. So if you do opt to fine-tune, which may improve performance so that you can compete with some of these bigger large language models, you'll be able to do that with relative ease compared to some of the bigger models. If you are interested in looking more into Bert, I'd recommend looking at SentenceBERT, as that's a good place to get started. I will say that for information retrieval, it seems that large language models are really a huge step forward, both just from looking at how they perform as well as seeing in papers how they perform on some common data sets. So that's really nice. However, I don't want to give the illusion that these are perfect and they'll solve all your problems immediately. To this end, let's kind of look at maybe one issue that you might run into with large language models. Now this really might be more of an implementation kind of obstacle that you have to overcome, but it's worth mentioning in either case. So one issue is that LLMs can really only process a limited amount of text at any time. Now this can be really large. Say for GPT-4, it can get I think around 128,000 tokens. So that's quite a bit of text. However, you might find that inputting that amount of text into information retrieval problem may give bad results. But anyways, it's still impressive that it can handle that much text, somewhat effectively. So let me dwell on that point a bit more. So really, if you input a ton of text, say 100,000 tokens, and there's some small little fact inside of it, the vector embedded may not really be able to capture that small little factoid inside. You may have better luck by, say, inputting the paragraph around that fact in order to get an effective information retrieval system. So then the question is, how small should I be, chunking the text? And the answer is really, it depends on your problem and it depends on your data and what large language model you're using. But, as a starting point, think around say 250 words. So one technique might be to split your, corpus of text into chunks of say 250 words and then use that to create your embeddings. That's a good starting point. You'll need a bit more sophisticated techniques in order to get good results, but at least that gets you kind of thinking in the right direction in terms of chunking the text. I will say, kind of curiously, you could actually use a large language model itself to aid in the process of chunking the text. So you could give it a large amount of text and say, hey, look, I need to chunk this in order to fit into another large language model and see what it gives. This is an important point in that large language models can be used to automate other processes that aren't necessarily, say, a chatbot like ChatGPT, but really used to kind of automate some of the more mundane tasks of, say, chunking text. And it's not just automation, because of course automation is easy in this problem, but it's really automation with the kind of understanding of the text that you're working with. All right, so to recap, we introduced the problem of information retrieval. This is the problem of given a query, figuring out which parts of a large corpus of text are relevant. We briefly talked about how some of the classical methods are limited in this respect. And we talked about how LLMs open up new ways to go about information retrieval. All right, that's it for this one. I hope you liked it, and I'll see you in the next one.